So in 5.2, what we're doing is balancing equations, but we're doing so with redox in mind. Meaning, it's not just the atoms that we're balancing anymore. Now it's actually looking at how many electrons are gained and how many are lost, and making sure that they are the same. And why is that important? Why do the number of electrons gained and lost need to be the same?
They have to go somewhere.
Yeah, they gotta go somewhere. It's the law of conservation of matter. So if something loses 2 electrons, those 2 electrons must be picked up by something. And so that's what we're gonna show in these reactions. So we're looking at the number of electrons gained versus lost. There is a different approach if you're talking about a molecular equation versus a net ionic equation. And that's where these approaches like the oxidation number method and the half cell reaction method come into play. But I'm striking the oxidation number method. That one's for molecular. It's just because you don't really ever see these. And like I can almost bet money that when you get into your freshman year and when you do redox, you're not going to see a single molecular equation. Okay? Like 99% sure. So we're going to focus on net ionic equations. So pretty much every equation you're going to see is going to have ions. And then, some neutral items too, but as a net ionic equation. Okay? And we're going to start with them being in an acid solution. So it will always indicate if it wants you to balance them in an acidic solution or a basic solution. And today we're going to focus on acidic. Believe it or not, I think acidic is harder. So once you do basic, you'll think it's a piece of cake. So when you see a net ionic equation, which I'm telling you, you pretty much always will be, you're going to use what's called the half cell method or the half cell reaction method. And a half cell is 2 half reactions. The reason that they're called half is because each one comprises half of the redox. One is reduction and one is oxidation. So they each represent 1/2 of the redox process. So what we want to do, I'm not sure if I put the steps here or not. Remember, it's reactions that are going to take place as a net ionic, which basically means in solution. And so you're going to have an acidic solution or a basic solution. And today we're going to specifically focus on acidic. So it will say that. It will say that to you. Balance the following redox equations using the half cell method in an acidic solution. So your professor or whoever it is should indicate to you, first of all, what method they want you to use, bless you, and then what kind of solution you have. Okay, so here we go. We are just going to, what's wrong?
You got a good cart.
Oh, cart. Yeah, one of those little buggies.
Yeah.
Brilliant. Okay. So, these are the steps, and then we're going to do a couple. You guys are going to find, this is really easy. So, first you have to assign oxidation numbers, because you want to figure out what's being oxidized and what's being reduced. As you get the hang of this, it'll be a lot easier to just kind of predict what's going to do that. So you'll be able to say, like, oh, I know that it's probably not hydrogen, for example. But at first, you'll probably have to go through and do every single one, which is why we did all the rules and practice knowing what the oxidation numbers are. So first, you guys got to see, okay, what is oxidized, what is reduced? Step number 2. Oh, wow, that's a big blob altogether. After you write the whole thing out, and usually that's going to be given to you, you're going to write 2 separate half reactions. And this probably just seems like gibberish right now, but we'll use them to do the 2 examples, and hopefully it'll make more sense. When you write the half reactions, you're going to include the entire species of whatever is being oxidized or reduced. So the whole thing. You're just going to pull it right out of the equation and plunk it down underneath. And then you're going to balance everything in that half reaction except for the O's and the H's, specifically whatever is being oxidized or reduced. 3 is invisible. 3 is do a happy dance. Aaron, I know you'll be right on that. And then 4, after your happy dance, you're going to multiply each of your half reactions by whole numbers to make your electrons gained and lost the same. So this is really the balancing part. This is really where you say, okay, well this one lost 5 and this one gained 2, so I got to balance that out. And so you just go through and you multiply the entire reaction by a whole number in order to do that. That's funny that there's no 3. Okay, so here is the... No, it actually should be like 5A, I guess. No, this comes next. This is in order. Henley, I have no idea. I can't explain myself. So this is next. If you have an acidic solution, so maybe we should just, here, just so nobody like freaks out here. 5, there. Okay, well we have a 4 already. So what's worse, really? Okay, but it's a happy dance. I'm recording these for the calculus people. They're going to be like, what in the heck is going on?
Right now?
Yeah, right now.
Oh. Hi, calculus people.
Everybody say hi, calculus people.
Hi, calculus people.
Yeah, they're going to be like, whatever. Okay, so 5A, if you have an acidic solution, which is what we're going to concentrate on today, you can use water to balance your O's. So as many O's as you need, just add that many waters. That's probably going to mess up your H's because every time you add an O, you add 2 H's with water. So then you can use the H pluses because you've got all kinds of acidic solution to balance out that part. And then voila, you're done. Now I'm wondering if there's another step that I added. The next step call it 6, which is to just add up your separate half reactions. This should remind you a lot of a net ionic equation, actually. So just like way back in the day when we took our net ionic equations and we added everything together, canceled out our spectator ions. That's the step 6, and then you have an overall equation at the end that you can circle, and it's perfect and it's wonderful. General rule of thumb is that transition metals like to change. So if you see a transition metal, the odds are ever in your favor that that will be something that's changing. Okay, do I have anything else? Ready to rock and roll? Yeah? What we got?
The H is +1.
Yes.
And the SO3 is -2.
The whole thing is -2, but we need the S and the O separately.
S +4. Yeah.
+4?
Minus O -2.
Okay. Now another good rule of thumb is that remember how O is like always -2, except for peroxides? So it's very likely that O is not going to change. Just like it's very likely that H is not going to change. Now that doesn't mean it's never going to change. It just means it's like bottom of the list for changing. Okay, Mn plus 2. I wanted to point this out to all of you guys because this is something that I meant to bring up on whatever day we talked about it first and I just forgot. Mn plus 2 is not a free uncombined element because it has a charge. So it's an ion, which makes you want to use rule number 2. It's a monatomic ion and it has a +2 charge, so therefore its oxidation number is also +2. Okay? If it was just Mn, nothing, it would be 0. Okay, but since it has an actual charge on it, its oxidation number is +2. All right, now you guys over here, what do I have for HSO4 -1, the bisulfate ion?
H is 1.
Yep.
S is 6.
Okay,
And O is negative.
beautiful. Okay, I like all of those. And now immediately you guys should spy 2 things that are changing. So we've got, I'm going to use a different color. I've got manganese. Oh, what's going to show up on here? Let's try green, see what happens. Manganese going from +7 to +2. Would that be oxidized or reduced? Yes. When its oxidation number actually goes down, it is reduced. The oxidation number itself is reduced. So I'm just going to write a little R on that line to remind myself. R. And that's more, you guys don't have to do this. You guys know I'm visual, so that helps me. Okay, and what else? What's your other half? Like, where's the oxidation happening? Yes, your sulfur is being then oxidize. So let's take a look at that. I'm going from +4 to +6. So yeah, my oxidation number is going up, meaning I'm losing electrons. So that's my oxidation number, or my oxidation. So what we want to do is take these out of the net ionic equation and write them as separate half cells. And generally speaking, your oxidation is always written first. There's a reason for that we're going to talk about later. But generally speaking, you don't do it wrong if you do the oxidation number second. It doesn't mean you're wrong. It's just traditionally how it's done. So we take our whole species that's being oxidized. That is the entire H2SO3 clump. And then we write the entire species that S is in on the other side, which is the entire HSO4 minus 1 clump. Okay, and so now we're on step 2, I think, which is what?
After writing the net ionic equation, write separate half reaction.
Okay, so here's my first half reaction. It's my oxidation half reaction. I like to also keep, since sulfur is the thing that's changing, I like to keep sulfur's oxidation number next to it. So there's +4 and there's +6. What you want to do at this point is make sure that the same number of sulfurs are on each side. So since sulfur is the thing that's changing, we want to make sure that if there's 2 on the left, there would be 2 on the right for it to change into. So we have 1 on the left and 1 on the right, so we're good. Okay, the next thing we want to do is show how many electrons are being lost in this process. So from left to right in oxidation, how many electrons are we losing? 2 total, right? We want that to be a total number, and so we show them separated by showing them over here. So we're going to get HSO4 and 2 electrons that are liberated, like leaving the scene. They are separate now. Okay, now I'm going to go ahead and do the same thing for the reduction portion. So my half cell reaction for the reduction portion, I'm going to take that whole MnO4 minus 1 out. And then over here on this side, which is kind of weird, but it's fine, the entire species is just Mn plus 2. But remember, don't worry, we have lots of O's and H's to play with if we need to balance them later. So over here, my Mn was +7. I'm just going to keep that there. And over here, it's +2. Kind of redundant, but I'm writing it again. Again, always check for if it's manganese that's changing, we want to have the same number of manganeses on each side. That sounds like a Dr. Seuss thing, manganeses. And we do. We have 1 of each, so we're good. And then we want to show how many electrons need to be added to MnO4 minus 1 to get to Mn plus 2.
What if they weren't balanced?
We're going to do that next. So we would just balance them. Just like a normal, we just put a coefficient in front of 1 to make them the same. Good question. Okay, so how many electrons do I have to add over here on the reactant side to get to Mn plus 2? 5, yeah, so 5 electrons plus that manganese MnO4 minus 1, the permanganate ion, is going to leave you with Mn plus 2. Okay, so obviously we have a problem. We have something that's liberating only 2 electrons and then something that's picking up 5. So that ain't going to work. So we're going to have to fix that, but remember that comes later. So we are on now step 4, I believe. Maybe it's 2. Where are we at? Where do we leave off? We wrote our 2 separate half reactions on what?
Multiply each. Happy dances.
Oh, happy dance. Sorry, everyone did it. Tyler, are you happy dancing? No, he's not happy dancing. Can't do the next step until you happy dance. So I'll tell you. Okay, then what?
Multiply each half reaction by numbers.
Okay, did we skip the step where we got to do H's and O's for acidic solution?
Oh, that's wrapped up into.
Oh, that's why it's 3A. Okay, because it's supposed to be 3A. All right, don't even. Stop it. So your 3A is really supposed to be right in there. So 3A comes before you multiply. Don't even go there. Just change it to 3. So we are going to add in step 3A, which was formerly known as 5A. the correct number, we're going to balance everything else out. Okay. So starting with the top, do O's first. O's on the left are, how many O's on the left?
3.
3. O's on the right are, so I need an extra O. So I'm going to add in over here. This is going to get a little messy. I'm going to add in an H2O. So now I will have the 3 from the SO3 and one more to make 4. So O's should be balanced. Okay. Now you can do H's. And so on the left versus the right, start with the left. How many H's on the left do you have? I think I heard someone say it, but I'm not sure.
4.
Yeah, you have the 2 from the water, and then you have 2 from the H2SO3. That's 4. On the right, you have 1, so you need 3 more. So you're just going to say, and 3H plus. You can do that, because you have all kinds of H plus, so that means, you know what, you're going to liberate 3 H pluses in the process. You can do that. You have an acid. It's fine. And it's going to require 1 water, but you're in solution, you have plenty of water to work with. Okay, same thing on the bottom now. O's. On the left you have 4. On the right you have none. So we're going to add in 4 waters. So on the right, or excuse me, I don't get my right and left mixed up. This is not good. I have my numbers and my sides mixed up. So on the left side, what we got to do? Not 4, careful.
8.
Got to do 8, yep, because we have 8 altogether and none on the left. So we got to have 8 H pluses. Okay, so now we can multiply by whole numbers. So what do I need to do to get my electrons to be the same coming and going? The top needs to be multiplied by 5. That gives me 10. I'm trying to show this in parentheses, but I'm running out of space. And so that means every single thing in that is going to have 5 times as many as we originally wrote. And then down here, 2, so that we have 10 electrons coming, 10 electrons going. Okay, so I need to write smaller next time. People do this in one of 2 ways. Some people like to just distribute like their 5 and their 2 all the way through everything and just cross things off. Some people like to rewrite the entire blessed thing. I am more of the distribute. It gets messy, but I'm lazy. So you can do it however you want. But what we want to do is get that 5 distributed all the way through, the 2 distributed all the way through, and then look at what we can cross off on each side. So for this example, because mine is so horribly messy, I'm going to have you guys help me, and I'm going to write the whole thing out this time to show you how it works. And then, I mean, you guys don't have to do it that way from now on. You can do it however you want, but then we can write the overall equation. So let's distribute all the reactants first. Okay, so you help me because this is going bye-bye. Okay, here we go. If I distribute that 5 through on the reactant side, what do I get? Just reactants. First equation. Should be 5 waters, right? Okay, and what else? 5 H2SO3s. Anything else on the reactant side for that one? Okay, let's go ahead and do the reactants for the bottom one then. 2 permanganates and
10 electrons.
yeah, I was gonna say I should have some electrons in there. Anything else? Are we good?
16 H plus.
16 H pluses. So we're just gathering all of our reactants after they've been distributed. Anything we're missing? No? Okay. So we'll do the same thing for the products. Okay, let's do the top first. Distribute that 5 through. Tell me what you get for your products. Top reaction. 5HSO4 minus 1. Okay. 10 electrons.
And 6 H pluses. Or wait, no, 15 H.
15 H pluses. Okay. Is that it for the top? Okay, bottom. 2Mn plus 2. 8 waters?
Yeah.
Okay. That it? Okay. Okay, so now think net ionic equations. Now that I've clumped all these together, you can look for things that are identical on both sides, and you can cancel one for one. So I always look for waters first because you usually have waters on both sides. So if I have 5, well, it should be on the left, mine's on the top. 5 in your reactants and 8 in your products, 5 of those are going to cancel, and you'll be left with 3 over here. You guys see how that works? Okay, so you'll have overall 3 waters created. 5 used, 8 made, so 3 overall. The next thing to always look for is your acidic hydrogens, your H pluses. So those usually have some canceling to do as well. So I have 16 in the reactants, 15 in the products, so that means all but 1 are going to cancel. So you have 1 more in the reactants than the products. 16 versus 15. And then last, I always double check my electrons. They should be exactly equal so that you know you've done it correctly. So your electrons should just be gone. And then we should be good. So you can rewrite this, or you can just call it good. That's what I always did. But I want you guys to notice something. We probably, if you were just to balance this like normally, you probably never would have just put a 2 in front of the, or thought that you needed to put a 2 in front of the MnO4 minus 1 and the Mn plus 2 because they're already balanced. But because of the electron flow, we have to. And so, believe it or not, doing it this way is easier than sometimes the traditional way, because if you think about the electrons first, then it helps you out a lot. And all of a sudden, we have these H2Os and H pluses that we never had before. So that'd be really hard to predict without doing it this way.
So that's our final answer.
That is your final answer. I know. It seems like a lot of work, doesn't it? It goes a lot faster the more you do it. A lot faster. So there you go. Do you have a tremendous sense of accomplishment now? Yeah? Should? It's awesome. All right, let's do another one.